Welcome to Orbital Dynamics, Part 62. 10 years after special relativity, Einstein published his theory of general relativity, which characterized gravity. It's a geometric theory of gravitation, and is the current description of gravitation in modern physics. It generalizes special relativity and Newton's law of universal gravitation. The basis of general relativity is Einstein's equivalence principle. Imagine a ball falling towards Earth at 9.81 meters per second squared. Now imagine a spaceship accelerating at 9.81 meters per second squared that has a ball inside that's stationary relative to us. We're observing this from an inertial frame of reference where we're not accelerating. Now let's look at this within each frame of reference. In both frames of reference here is what each observer observes. The ball falls in both cases. Galileo suggested that you get the same results from kinematic experiments in any inertial frame of reference. That's a frame of reference that is either at rest or moving at a constant velocity. Einstein's equivalence principle suggests something similar in a non-inertial frame of reference. In both these accelerating frames of reference, you'd also get the same results from kinematic experiments. On the surface of the Earth, you'd experience a 9.81 meter per second squared acceleration downward. Likewise, on a spaceship, accelerating at 9.81 meters per second squared, you'd also experience an apparent 9.81 meter per second squared acceleration downward. If you were inside a box with no windows, you wouldn't be able to tell if you were on Earth or in a spaceship. You'd feel a downward force of 9.81 meters per second squared in both cases. Notice that in the case of the spaceship, the ball doesn't move. It is in its own inertial frame of reference. The ball doesn't fall. The floor of the spaceship moves up to meet it. Since the spaceship is accelerating, the floor moves up more rapidly as time passes to meet the ball. On Earth, we've said that the falling ball is in a non-inertial frame of reference because it's accelerating downward. What if the box had no windows? In both cases, the ball falls downward at 9.81 meters per second squared. But in the one case on the spaceship, the ball is in its own inertial frame of reference, and in the other, we say it's accelerating. Einstein suggested that the ball falling towards the Earth would also be in its own inertial frame of reference. You have to think of this from the perspective of the ball. An inertial frame of reference implies there's no acceleration, and Einstein was suggesting that there isn't any acceleration imparted on the ball that's falling toward the Earth. This contradicts Newton's law of gravitation. In Newton's mind, he conceived a force to account for the motion of planets around the Sun and balls falling towards Earth. The law of inertia states that a body in circular motion has to have some force to keep it in circular motion. Otherwise, it wants to travel in a straight line. Einstein turned that theory inside out. We've talked about the difference between mass and weight. Weight is a measure of acceleration. If you're in free fall, you're weightless. If you jumped off a high cliff with no air resistance, which is very hypothetical on Earth, you'd stay in free fall until you hit the ground. When Einstein realized that an object in free fall is weightless, it was supposedly one of the most incredible experiences of his life. He understood something for the first time that probably no one else understood. We can confirm this equivalence principle if we think about how it feels to have a force acting upon us. Newton's first law and Galileo's law of inertia states that an object either remains at rest or continues to move at a constant velocity unless acted upon by an external force. A force acting on an object is equal to the mass of the object times the implied acceleration. We've all felt acceleration that results from a force. When we're accelerated, we can feel it. It feels like a push or a pull. In a car, when the driver hits the gas, the acceleration puts us in the back of our seats. On the other hand, a braking action propels us forward. Same is true when a plane takes off and lands. In free fall, however, we feel weightless. We don't feel any force acting upon us. We don't feel a force until we hit the ground. The force we feel while standing on the Earth is the mechanical structure of the Earth holding us up, not the force of gravity. Gravity expressed as a force is a fictitious force like the centrifugal force. The acceleration that is felt in the presence of gravity is felt when something like the surface of the Earth holds you against gravity. In the spaceship, it's the ship that accelerates. You feel the force of that acceleration through the floor of the spaceship. That's what imparts a force on you. On Earth, it has to be the same. It's the surface of the Earth that imparts a force on you. Now let's shine a light from one side of the spaceship to the other. From our inertial frame of reference, it started here and ended here. If you were on the spaceship, you'd see something like this. This only occurs because the spaceship is accelerating. The beam is turned on in one instant, but it takes time for it to hit the wall. In the meantime, the spaceship is accelerating before the light gets to the other side. If the spaceship were in an inertial frame of reference, not accelerating, the beam would go straight across. It's only when it's accelerating that you see this deflection. If the spaceship, accelerating at 9.81 meters per second squared, is equivalent to being on Earth, then you'd observe the same phenomena on Earth. A massive object like the Earth creates a gravitational field, and that will deflect light. Einstein predicted this in his theory of general relativity. Einstein suggested that a gravitational field would affect the propagation of light or any electromagnetic radiation. He published General Relativity in 1916. 3 years later, there was a total solar eclipse. During a total solar eclipse, the light of the sun is obscured, allowing you to see stars that are very close to the sun. Say there was a star depicted by A behind the sun. In this diagram, you can see the light from star A traveling around the sun through curved space-time. To an observer, the star would appear to be at location B. Sir Arthur Eddington, one of Einstein's contemporaries, took measurements during the solar eclipse in 1919. Stars near the sun appeared offset. This was spectacular news and made the front page of many major newspapers. It confirmed Einstein's theories of special and general relativity and instantly made him world famous. If you were to plot escape velocities for the Earth, it looks like this. A spaceship at the surface of the Earth must travel 11.19 kilometers per second in order to escape Earth's gravity. As the ship gets away from the Earth, the escape velocity decreases. Gravity diminishes with 1 over r squared, which is the distance from the center of the Earth. Since gravity is not a force, how should we think of gravity? This curve lends a clue. Imagine the mass of the Earth at the bottom of a well that is shaped along the escape velocity curve. This analogy is not correct from a kinematic sense, but nevertheless makes the point. If we wanted to travel around the steep part of the well, we'd have to travel very fast. Otherwise, we'd fall in towards the mass of the Earth. If we're farther away from the Earth, the slope of the well is much more shallow. We don't have to travel as fast in order to circle the well. In fact, if we travel too fast, we'd careen off to infinity. Imagine a trajectory like this one. When an orbiting object approaches the steep part of the well, as it descends, it will pick up speed. It'll then whip around and be kicked out to the more shallow part. As it rises up the well, it will lose speed, and on the more shallow part, it will gradually come back around. This characterizes the timing of an elliptical orbit and demonstrates that a planet must travel faster when near the central body, at perigee, in the Earth's case, and slower when further away at apogee. If the planet doesn't go fast enough in the steep part, it will fall to the bottom of the well. That's analogous with crashing into the Earth. If it travels too fast on the shallow part, it will careen off. That's analogous to achieving escape velocity. If the satellite is to gain altitude, it has to climb up the gravity well. Einstein suggested that any object with mass distorts space, and he referred to this distortion as a curvature of space-time. Gravity is thus a purely geometric consequence of the properties of space-time around a massive object. Gravity in general relativity is described in terms of curved space-time. Matter tells space how to curve, and curved space-time tells matter how to move. When a body in motion moves through space-time, it takes the shortest path that's defined by the curvature of space. If you've traveled long distances on the Earth, you've traveled over routes that are geodesics. On a Mercator projection, as you can see on the left, it might seem that the shortest distance from Los Angeles to Tokyo is right across the Pacific Ocean. On a globe, however, you can see that the shortest path takes you higher to the north. Curved spacetime follows the same principle. Planets, when they orbit the sun, do not want to go in straight lines. They want to follow the shortest path through curved spacetime. The flight route on the right goes along a geodesic. Same goes with planets moving in spacetime. They travel along geodesics. The definition of geodesic is the shortest possible line between 2 points on a curved surface. There's another effect that general relativity predicts: gravitational time dilation. Imagine an electromagnetic wave emanating from the surface of the Earth straight out into space. If light waves are deflected as they pass through a gravitational field, then they must be elongated as they attempt to get out of the gravitational field. Light, when it climbs through a gravity well, gets elongated. It loses energy. Light that was blue at the surface will shift into the redder part of the spectrum on the way out. Blue wavelengths are smaller than red. Let's say the observer on Earth counts the number of waves that pass here and compares it to his clock. Let's say one wave passes every second. Now let's put an observer in space where the waves are elongated. Now let's say there's one wave every 2 seconds. The guy in orbit sees an event every 2 seconds that the guy on the surface sees every second. The guy in space sees another form of time dilation. The guy on Earth appears to be going in slow motion at half speed. Looking the other way, the guy on Earth would observe the guy in space going in fast motion, twice as fast. This is the GPS constellation of satellites. They orbit in circular medium Earth orbits at an altitude of about 20,000 kilometers. Remember from special relativity that time will dilate on the satellite due to the velocity of the orbital motion. The gravitational effect does the opposite. From our perspective, on Earth linking up with GPS satellites, the clocks run faster. Velocity dilates time and less gravitational potential speeds up time. Which phenomena dominates? For GPS, it's gravity. Accurate time is vital for navigation. GPS satellites have very accurate atomic clocks on board. In order to stay in sync with clocks on the ground, however, they have to be slowed down. There's a wonderful comic strip, XKCD, by Randall Munroe. He warns you that some of his content contains strong language. What I'm showing you here doesn't. He has a degree in physics and used to work at NASA. He understands these theories. He drew the gravity wells of the planets. The sun is so huge that he didn't have room to show it. It's way down on the left-hand side of the diagram. You can see the inner planets on the left: Mercury, Venus, Earth, and Mars. Jupiter is the most massive, so its gravity well is deep. Saturn is also fairly massive. Then there's Uranus and Neptune. You can think of escape velocity as the energy it would take to climb out of these wells. Let's zoom in on Mars. Here you can see the two small moons of Mars, Deimos and Phobos. Munroe says that you can climb out of the Deimos gravity well with a bicycle and a ramp. On Phobos, you could literally throw a baseball into orbit. You could play catch with yourself. Here's the Earth. You can see the satellite regimes: low Earth orbit, where the International Space Station is; medium Earth orbit, where GPS is; and geosynchronous orbit, where many of our communication satellites are. In order to get to the moon, astronauts had to climb out of the steepest part of the Earth gravity well and then go a little bit way back down to the moon. They needed a huge Saturn rocket to do this. To get back to Earth, all they needed to do was climb the gravity well of the moon, a much easier feat, and from there the way home was downhill. We derived the formula for escape velocity in a previous section. It's the square root of 2gm over r. The escape velocity for an object at the surface of the Earth is 11.19 kilometers per second. What if the escape velocity were 299,792,458 kilometers per second? That's the speed of light, and nothing can go the speed of light except electromagnetic waves. This is an escape velocity that a massive object can never reach. Here's an equation with this hypothetical escape velocity. Let's square both sides so we can get rid of the radical, and then let's express this in terms of the radius r. Any massive object that is less than this radius will require an escape velocity at the surface that is equal to the speed of light, and nothing with mass can go that speed. Anything with a smaller radius would have to exceed the speed of light, and nothing can go faster than the speed of light. If we consider the mass of the sun, the radius would be 3 kilometers. If we were to compress the mass of the sun into a sphere that was 3 kilometers, then the escape velocity at the surface would be c, the speed of light. Here's what we get for the Earth mass. If we were to compress an Earth mass into a sphere with a 9 millimeter radius, then the escape velocity would be c, the speed of light. This radius is called the Schwarzschild radius. More massive objects have a longer Schwarzschild radius. Less massive ones have a smaller radius. The Schwarzschild radius is the demarcation where an event horizon forms. If you go inside it, you will never get out, since you cannot exceed the speed of light. Any electromagnetic radiation will be trapped too. This is the formal definition of a black hole. Anything that goes in will never come out. Because of the event horizon, a black hole looks like a void. It does, however, have properties and structure. Black holes, by the way, do not vacuum up matter. If the sun were compressed down to a 3 kilometer radius sphere, the planets would still remain in their elliptical orbits. Black holes only consume matter that is on a collision course. Only matter that falls into the gravity well, not matter that has enough velocity to orbit.